Hello, and welcome to the lecture on 10.4. Today we're going to talk about the algebra of matrices. Let's start with what it means for two matrices to be equal. Quality of matrices. The matrices A equals Aij and B equals Bij are equal if and only if they have the same dimension, m by n, and corresponding entries. What that means is Aij is equal to Bij for every inj. For example, find x in these two matrices. So, right here what we're saying is that these two matrices are equivalent. This means that they must be the same size, so they have the same number of rows and the same number of columns, which is 2 by 2 and 2 by 2, so that's true. And they also have to have identical entries, meaning that the first term, a sub 1, 1, has to equal b sub 1, 1. A sub 1, 2 has to equal b sub 1, 2, and so on. So if we're looking for x and we have these two identical matrices, then we know x squared is equal to 4 and x plus 1 is equal to 3. So if we solve both of these equations, we get x is equal to 2 and x is equal to 2 or x is equal to negative 2. So what's our solution? Is our solution 2 or is our solution 2 and negative 2? We have to think about this for a second. Remember that when we have a solution, it needs to be true for every x. So if I plug in an x here and here, it needs to hold equality for this matrix. So if I plug in a 2, I get 2 squared is 4. That's fine. 1, negative 2, and 2 plus 1 is 3. So 2 definitely works. Now let's check negative 2. If I plug in negative 2, I get negative 2 squared, which is 4. That's fine. 1, 1, negative 2, negative 2. And then negative 2 plus 1 is negative 1. But that's not equal to 3. So negative 2 is actually not a solution in this case. So only x equals 2 is a solution, because it needs to work for every single x in the matrix. All right, the next topic is going to be addition, subtraction, and scalar multiplication of matrices. Some difference in scalar product. Let A equal Aij and B equal Bij be matrices of the same dimension m by n, and let C be any real number. 1. The sum A plus B is the m by n matrix obtained by adding the corresponding entries of A and B. A plus B equals Aij plus Bij. Now what we're saying here is that when you add two matrices together, they need to be the same size, first of all, and then what we do is add each corresponding entry. So A11 adds to B11, A12 adds to B12, and so on. If they're in the exact same location with respect to their matrix, then we add them together if we're looking for the sum. 2. The difference, A minus B, is the m by n matrix obtained by subtracting the corresponding entries of A and B. So A minus B equals Aij minus Bij. Now, this is done exactly the same way. If they're in the exact same location within their respective matrix, and we're subtracting A minus B, then we subtract those entries. So again, A11 will subtract from B11. A12 will subtract B12. A45 will subtract B45, and so on, for every single entry within the matrix. The scalar product, C times A, is the m by n matrix obtained by multiplying each entry of A by C. So it'll look C times A is equal to C times Aij for every single ij within the matrix. I'm going to do an example of each of these so that we can sort of see how they work. They are pretty intuitive, especially addition and subtraction. Let's say that A is equal to 1, 2, 3, 4, negative 1, 5. And B is equal to 2, negative 3, 4, negative 1, 1, and 5. A plus B, we take each entry location and we add the respective entries together. So the entry in row 1, column 1 will add to the entry in row 1, column 1. So here in A plus B, we would have 1 plus 2, which is, we take the entry in row 1, column 2, and add it to row 1, column 2 in the other matrix. We would have 2 plus negative 3, which is negative 1. 3 plus 4, 7. 4 plus negative 1, 3. Negative 1 plus 1, 0. 5 plus 5, 10. This is how we add two matrices together. We just take each element and we add it to the same exact position in the other matrix. Now if we do 3 times A, we take 3 and we multiply to every entry in A. So 3 times A will be 3 times 1, which is 3, 3 times 2, which is 6, 3 times 3 is 9, 4 times 3 is 12, 3 times negative 1 is negative 3, and 3 times 5 is 15. And we get this matrix. Now I want you to try one as well. Find A minus 2B. So here, you're going to want to do order of operations also. So I didn't do the subtraction, but you need to multiply B times 2 and then subtract this matrix from A. So you'll do A minus 2B. Properties of addition and scalar multiplication of matrices. Let capital A, B, and C be m by n matrices, and let C and D be scalars. Then we have A plus B is equal to B plus A. This is called the commutative property of matrix addition. Now remember, a long time ago, at the beginning of this class in chapter 1, we referenced addition, subtraction, multiplication, and division as operations. We said we had inverses and we had identities and so forth. Here, we're doing the same thing, but instead of referencing addition, we have to specify the type of addition as matrix addition. Because matrix addition and addition are different. They're not the same operation. Namely that a matrix addition takes two matrices to add together. Regular addition takes two numbers and you add them together. But the properties usually are named the same, like commutative and associative and distributive. 2, A plus B plus C is equal to A plus B plus C. This is the associative property of matrix addition. Same as the associative property of regular addition, insofar as we can add the respective elements in any order. So A plus B, matrix A plus matrix B can be added before we add C, or we can add B to C before we add A. It doesn't matter what order you add in. That's the associative property. Now we specified again with matrix addition because we are applying this property specifically to matrix addition. So here we have two scalar numbers, C and D. And if we multiply D times A and then multiply C times the result, it's the same thing as multiplying C times D, the two scalars together, and then multiplying by A. Now this is the associative property of scalar multiplication. Again, we specify that it's scalar multiplication to indicate that it takes a number and a matrix, and we're multiplying a number times a matrix, and not a number times a number. If it was just a number times a number, then it would just be multiplication. But because we have a number times a matrix, it's scalar multiplication. But the associative property, like before, is basically the same. You can multiply in any order you want to. C times D first, or D times A first, and then C times the result. And 4, we have C times A plus B is equal to C times A plus C times B. Now this is the distributive property of scalar multiplication. What it means is if we have C times a sum of two matrices, then we can distribute this scalar C to A and to B, just like we normally would with other with regular numbers instead of matrices. 5 is the other version of the distributive property. Suppose that we have two scalars that are being added together, c plus d, and we're multiplying it by a matrix. Then this would we can still distribute the matrix A into the sum of the two scalars. So c times a plus d times a. This is also the distributive property of scalar multiplication. Let's go ahead and do an example here and sort of show what we can do with these. So suppose that we have 2x matrix x plus a is equal to b, where a is equal to 1, 3, negative 2, 4, and b is equal to 5, negative 1, 8, and 2. Now, how would we solve this? We'd basically solve it the same way we would solve anything. We're looking for a matrix X, and we have two knowns, A and B here. We just need to solve for X, like normal. So here, we would subtract our A, so 2 times X is equal to B minus A. And we know what B and A are, so we can figure out what B minus A is. So let's figure that out first, and then we'll deal with this too. B minus A, we would have 5 minus 1, which is 4. Negative 1 minus 3 is negative 4. 8 minus negative 2 is 10. And 2 minus 4 is negative 2. So we have 2x is equal to this matrix. Now, if I multiply both sides by 1/2, then I've solved for x. So I would have x is equal to 1/2 of this matrix. So we multiply each entry by 1/2, and we get 4 divided by 2, which is 2. Negative 4 divided by 2 is negative 2. 10 divided by 2 is 5. And negative 2 divided by 2 is negative 1. So now we have x, and that's what we were looking for all along. Right, the next topic I want to talk about is multiplication of matrices. Now, this topic is actually pretty tricky, so we're going to spend a little bit of extra time on this. Note, multiply two matrices A and B, the number of columns of A must match the number of rows of B. So suppose that we have A is an m by n matrix, and we wanted to multiply B, which is an n by p. This is okay because the number of columns in A is n, and the number of rows in B is n. These two match. Since they match, we can actually multiply these two matrices together. It does not matter how many rows A has and how many columns B has. It only matters that the number of columns of A matches the number of rows of B. And this is very, very important. Let me show you why. Let me show you an example here. So suppose that we have A is equal to 1, 2, 3, 4, and B is equal to 1, 2, 3, 4, 5, 6. Can I multiply A times B? Is this a possible multiplication? Well, A is a 2 by 2 matrix. B is a 2 by 3 matrix. So yes, we have 2 columns in A, and we have 2 rows in B. And once we get into the actual multiplication, you'll see why, or I'll try to explain why. Now, can I multiply B times A? This one we cannot do, because here, B times A, because B is a 2 by 3 matrix, meaning it has 3 columns, but A only has 2 rows. Because B is first in this multiplication, the number of columns of B must match the number of rows of A, and they don't. So BA doesn't exist, but AB does. if A1, A2, all the way up to AN is a row of A, and B1, B2, all the way down to BN is a column of B, then their inner product is A1, B1 plus A2, B2 plus all the way up to A sub n, B sub n. What we do is we take each element in the row of A and multiply it by the corresponding element in the column of B, and then we add the results. That's how you find the inner product of these two rows and columns respectively. For example, suppose that we had a row of A was 1, 2, 3, and a column of B was 4, 5, 6. Then the inner product of these two would be 1 times 4 plus 2 times 5 plus 3 times 6. We'd have 4 plus 10 plus 18, 32. Notice that we have a single number when we take the inner product of a row and a column. We get a single number back, right? It's the sum of the products of the respective elements. You take your first element, multiply it by the first element. Second element, multiply it by the second element. Third element, multiply it by the third element. And then you add those results. And now this is important because it plays an enormous role in matrix multiplication. If matrix A equals Aij is an m by n matrix, and matrix B is Bij is a n by k matrix, then their product is m by k matrix C equals Cij, where Cij is the inner product of the ith row of A and the jth column of B. We write the product as C equals AB. This is actually a pretty difficult concept for a lot of students to get and master. When we say an inner product, remember, we're multiplying something that looks like this. So we would get a row of A and multiply it by a column of B. But B will have k columns, and A has m rows. So we take each of the m rows and we multiply it by each of the k columns in B. And when I say multiply, I'm talking about the inner product. Let me give you an idea here. Let's do an example. Say that A is equal to 1, negative 1, 2, 2, 3, negative 2. And B is equal to 1, 2, negative 5, 3, 1, 0, negative 1, 2, 1. Say that we have these two matrices. Can we find AB? Yes, AB exists. Count the number of columns of A, we have 3 columns. Count the number of rows of B, we have 3 rows. They're equal, so AB exists. Remember, we count the columns of the first matrix in the matrix multiplication. And we count the rows of the second matrix in the matrix multiplication. Let's say that C is equal to AB. Okay. Now what I'm going to do is I'm going to do each one. Let's figure out what C11 is. So first, let me note how big C is going to be. Note that A is a 2 by 3 matrix and B is a 3 by 3 matrix. This means that C is going to be a 2 by 3 matrix because it's m by k, as I stated up here, m by k matrix. The number of rows from A and the number of columns from B. So C is going to be a 2 by 3 matrix. So I need to figure out what C11 is, C12, C13, C21, C22, and C23. I know where all these numbers are coming from because remember the first subscript is the row that this element comes from, and the second subscript is the column. I know I have 2 rows and 3 columns. So first row, first column, first row, second column, first row, third column. that would be the end of this row because I only have 3 columns. Second row, which is the last row because there's only 2 rows. Second row, first column, second row, second column, second row, third column. Let's figure out what C11 is. Sorry, remember Cij is the inner product of the ith row of A and the jth column of B in this multiplication, AB. So we take the ith row of the first one, multiply it by the jth column of B. So here, Cij, I is the first subscript, j is the second. Our first subscript is 1. Our second subscript is 1. So we're taking the first row of A, 1, negative 1, and 2, and multiplying it by the first column of B, 1, 3, negative 1. Again, we multiply their entries. 1 times 1 plus negative 1 times 3 plus 2 times negative 1 times 1 plus negative 1 times 3 plus 2 times negative 1. And what do we get? 1 minus 3 minus 2. We get negative 4. Now I take the first row of A and the second column of B because we're looking at C12. Again, Ij, ith row of A, jth column of B. And when I say A and B, it's only because A is first here and B is second. So we take the row of the first and the column of the second. We have first row of A, second column of B. So first row again is 1, negative 1, 2. Second column is 2, 1, 2. We have 1 times 2 plus negative 1 times 1 plus 2 times 2. We have 2 minus 1 plus 4. We have 5. Now C13 is first row of A, third column of B. The first row, third column. 1, negative 1, 2 times negative 5, 0, 1. And we multiply entry-wise. 1 times negative 5, negative 1 times 0, 2 times 1. 1 times negative 5, negative 1 times 0, plus 2 times 1. 2 times 1 is 2, negative 1 times 0 is 0, negative 5 times 1 is negative 5. So negative 5 plus 2 is negative 3. Now we're looking at the second row of A, first column of B. Second row of A, first column of B. 2, 3, negative 2. 1, 3, negative 1. This would be 2 times 1, 3 times 3, negative 2 times negative. So 2 times 1 plus 3 times 3 plus negative 2 times negative 1. 2, 9, 2. So 4 plus 9 is 13. Second row of A, second column of B. Second row of A, second column of B. So 2, 3, negative 2. Second column of B is 2, 1, 2. 2 times 2, 3 times 1, negative 2 times 2. So 2 times 2 plus 3 times 1 plus negative 2 times 2. Negative 2 times 2 is 4, negative 4. 2 times 2 is 4, so these two will cancel, and we're left with just 3. And C23 is going to be second row of A, third column of B. 2, 3, negative 2 times negative 5, 0, 1. 2 times negative 5, 3 times 0, negative 2 times 1. 2 times negative 5 plus 3 times 0 plus negative 2 times 1. We have a negative 10 minus 2 is negative 12 plus 0. So we have negative 12. So our matrix, our C matrix, we know what every single entry is. C11, C12, C13, C21, C22, C23. C11, that's first row, first column, gives me a negative 4. C12 is first row, second column, 5. C13, first row, third column, negative 3. C21, second row, first column, 13. C22, second row, second column, 3. And second row, third column is negative 12. So this would be our matrix C, which is the product of A and B. What about B times A? Well, we can't actually do this because B is a 3 by 3. It has 3 columns and A only has 2 rows. So let's try to. I want to show you why this is impossible. Let's try to do this really quickly. So if we said that C is equal to B times A, then we would be looking for C, a 3 by 3 matrix. So C11, and this should automatically just stop it from happening. So C11 would be the first row of B times the first column of A. So first row of B, 1, 2, negative 5, times the first column of A, 1, 2. So we would have 1 times 1, 2 times 2, negative 5 times nothing. There's nothing here to multiply by negative 5. So if we actually tried to do this, we would end up with negative 5 times something that doesn't exist, which makes this impossible. We can't take the inner product of these two things because their dimensions don't match. You have 3 elements here, and we only have 2 elements here. So this actually cannot work for this particular part, B times A. And we already know that it won't work because we have 3 columns of B and 2 rows in A. So if we were doing B times A, this would be a 3 by 3 times a 2 by 3. Notice that their interior dimensions do not match. 3 and 2, they don't match. So this doesn't work. It's non-existent. Try one on the accompanying worksheet. Let A equal 1, 2, negative 2, 1, and B equal 1, 5, 3, 0, negative 1, 1. And C equal AB. Find, you only need to find a couple of parts here, so just find C1, 2 and C2, 3. So you need to figure out which row of A and which column of B you need to take the inner product of. And that's all you need to do for these two entries. If you want to do the rest, I would encourage that. But it's not necessary for this particular exercise. Right, the next topic I want to talk about is properties of matrix multiplication. Let A, B, and C be matrices for which the following products are defined. Then A times B times C is equal to A times B times C. This is called the associative property of matrix multiplication. And B plus C times A is equal to BA plus CA. This is called the distributive property of matrix multiplication. Well, there's a couple things I want to say here really quickly. One, notice here in the distributive property that this is not A times B. When we distribute our A, it distributes on the right side of the product. So B times A and C times A. And that's because the other thing that you should notice, the commutative property of matrix multiplication does not exist. There is nothing here about being able to commute A and B. AB is not equal to BA. In a general sense, this is not true. Now, there are particular instances where it is true, but for the vast, vast majority of matrices, these things are not equal. All right, we cannot commute A and B in terms of multiplication. And this is where multiplication and matrix multiplication differ a lot, because regular multiplication with numbers, just ordinary numbers, is commutative, but matrix multiplication is not commutative. Let's do an example here and show you what these properties do. Let A equal 1, 2, negative 1, 3, and B equal 2, 1, 0, 1. Then AB is equal to 2, 3, negative 2, 2. For this first one, remember we take the first row of A, multiply it by the first column. So 1 times 2 plus 2 times 0, 2. 2 plus 0. The second here, this would be the entry first row, second column. So here. And then here, remember this is the first row, second column entry. So we take the first row, multiply it by the second column of B. First row of A times the second column of B. So we do 1 times 1 plus 2 times 1 gives us 3. Now here, this entry is the second row, first column. We're in the second row, but the first column. So we take the second row of A, multiply by the first column of B. Negative 1 times 2 plus 3 times 0, so negative 2. And then here, this is the second row, second column. So we take the second row of A, multiply it by the second column of B. Negative 1 times 1, 3 times 1. So we get a negative 1 plus 3 is 2. Now I want to show you what BA is equal to show you that these two matrices will not be the same. So BA, we're looking for the first row, first column entry. So we take the first row of the first matrix in the multiplication. So first row of B times the first column of A. Do 1 times 1, negative 1. 2 times 1 plus 1 times negative 1 will give me just 1. Right away, we can see that these two are not equal. The first entry is different. Let's finish just for the practice. First row, second column. First row B times the second column of A. 2 times 2 plus 3 times 1. 2 times 2 plus 1 times 3 gives me 4 plus 3 is 7. Now we're at the second row, first column. So we take the second row of B, multiply it by the first column. 0 times 1 plus 1 times negative 1. Just be negative 1. And then the second row, second column. So we take the second row of B, multiply it by the second column of A. 0 times 2 plus 1 times 3 gives me 3. These two matrices don't look anything alike, right? Now, this is to say that these two, A times B and B times A, are not equal. This means AB is not equal to BA. I want to emphasize this as much as I possibly can, because this is such a common mistake. Even beyond this class, this is a common mistake. The last topic I want to talk about is application of matrix multiplication. A system of linear equations can be written as a product of matrices. I'm going to show you sort of how this works with a quick example here. Suppose that we have a system of equations x minus 2y plus z is equal to 0, 3x minus y minus 2z is equal to 0, and negative x plus 2y plus z is equal to 2. Suppose that we have this. So remember, we can write the matrix, we can write out a coefficient matrix that would be have entries that are the coefficients of the right sides of the equations of this system. So our coefficient matrix in this case would be 1, negative 2, 1, 3, negative 1, negative 2, 1, sorry, negative 1, 2, 1. So we would have something that looks like this. 1, negative 2, 1, 1, negative 2, 1, 3, negative 1, negative 2, 3, negative 1, negative 2, negative 1, 2, 1, negative 1, 2, 1. This is the coefficient matrix. Now remember, each column corresponds to a specific variable. So we would have a matrix here, x, y, z, equal to, notice that if we were to do matrix multiplication, it would be 1 times x, x, plus negative 2 times y, negative 2y, plus 1 times z, z. And that would be equal to 0. Similarly, 3 times x, 3x, negative 1 times y, negative y, negative 2 times z, negative 2z, equal to 0. And negative 1 times x plus 2 times y plus 1 times z. Negative 1 times x plus 2 times y plus z is equal to 2. So this matrix multiplication is a representation of this system. So there is a way, and we'll talk about this later when we get into inverses of matrices, there is a way to actually solve this system by just doing a single matrix multiplication. Again, we'll talk about that later. The coefficient matrix, you have your variables and your solutions to the system equations, that is. This is an equivalent way to state this system. Now, in general, we would write such a system as a times x is equal to b. And now this is the foundation of linear algebra. When you go far enough in math, you'll get past calculus and you'll get into DE, and roughly around the time that you take DE, you can take linear algebra. And this is the foundation. We do a lot of linear systems just like this. Let me do an example really quickly of how we can use matrix multiplication in the real world. In this example, we're going to show you how you can organize data, and we can figure out a few things just by multiplying different matrices. The following table represents the proportion of clones that survived or died under a particular general. We have Skywalker, Novi, and Krell. 5. Skywalker had a 70% survival rate, means 30% died. Kenobi had a 60% survival rate, means 40% died. And Krell had a 20% survival rate, which means 80% died. The following table represents the number of arc/regular troops that served under each of the previous generals. Skywalker, Kenobi, and Krell. ARC troopers and regs. Let's say that Skywalker had 400 ARC troopers and 2,000 regs. Kenobi had 100 ARC troopers and 1,200 regs. And Krell had 200 ARC troopers and 5,000 regs. Okay, so this information is organized pretty nicely here, that we have the number of ARC troopers and regs that served under each general, and the survival rate for each general. Now, why are we talking about this in a multiplication of matrices type situation? Well, we can talk about this table up here as being a matrix A, and this table here being a matrix B. Now, when we multiply these two, what's going to happen is the Skywalker, Krell, and Kenobi aspect of these tables is going to go away. And we're going to see how many ARC troopers survived versus died and how many regs survived versus died just by having these two tables together. So, when we look at this and we do A times B, I want you to notice that A is going to be a 2 by 3 and B is going to be a 3 by 2. Now, we want to multiply Skywalker to Skywalker, Kenobi to Kenobi, and Krell to Krell. Otherwise, it doesn't really make sense. So when we multiply along the Skywalker, Kenobi, and Krell categories, those categories are going to go away, and what's going to be left is just survived, died versus survived and died, and ARC Trooper and Reg Troopers. So if we look at A, we would have 0.7, 0.6, 0.2, 0.3, 0.4, and 0.8, and we're multiplying by B, which is 400, 2000, 100, 1200, and 200, 5000. Now, when we multiply this, remember the category for columns here, Skywalker, Kenobi, Krell, and the category for rows here, Skywalker, Kenobi, Krell. When we do a row times a column, we're multiplying Skywalker times Skywalker, Kenobi times Kenobi, and Krell times Krell. We would do 0.7 times 400, 0.6 times 100, and 0.2 times 200. I'm just going to give you those numbers. We have a 2 by 3, and we're multiplying a 3 by 2. Just to make sure that we can actually multiply them, 3, 3, and we're going to end with a 2 by 2 matrix. Here in this very first square, we're going to end up with 380. This is row 1, column 1. So we take the first row, multiply by the first column. We're going to do row 1, column 2 now. So we do first row times the second column. This would be survival rate times the regular troopers. And we end up with 3,120. That would be 0.7 times 2,000 plus 0.6 times 1,200 plus 0.2 times 5,000. Now we do second row, first column. So we do our second row of A times our first column of B. And we get 320. And that would have been 0.3 times 400 plus 0.4 times 100 plus 0.8 times 200. Now we do second row, second column. So the second row of A times the second column of B. We're going to take 0.3 times 2,000 plus 0.4 times 1,200 plus 0.8 times 5,000. And that's going to be 5,080. Okay, now what does this mean? As I stated before, if we rewrite this as a table, we would have ARC Trooper and Regs. These would be our columns. And our rows would be survived versus died. We'd have 380 survived, 320 died. The regular troopers would have been 3,120 survived, and 5,080 died. Now I want you to notice a couple of things. First of all, these two numbers should add up to what these three numbers are. The number of regular troopers that were in the total system should be 8,200. And if we add these two together, we get 8,200. That was the total number of regular troopers. Similarly, the number of ARC troopers should add up. So 380 plus 320 should be the same thing as 400 plus 100 plus 200 is 700, and this would be 700 as well. So this is just the total number of ARC troopers that survived amongst all three generals. Total number of ARC troopers that died amongst all three generals. Total number of regular troopers that survived amongst all three generals, and the total number of regular troopers that died amongst all three generals. All right, that's going to be it for today. I will see you all at the next lecture.